This lecture is about entropy. It's a form of energy, and I love this image because entropy is the understanding of entropy is a huge misconception. You think of it as disorder. I think that's what textbooks say, but it really is not. It is the spreading out of energy, or the dilution of energy, and it's actually an energy term itself. All right, so we're going to talk about the first couple of laws of thermodynamics. The first law of thermodynamics, which you're probably all familiar with, is that the total energy of the universe is conserved. Okay, so we cannot create nor can we destroy energy. So, a kind of deep thinking question I like to pose to students when we talk about the laws of thermodynamics is that if all energy in the universe is conserved, then why are we so worried about running out of energy? Think about that for a minute. See if you have any idea, just kind of for fun. And then I'll talk about why that is. Okay, so back up for a minute. I did say that entropy is the spreading out or the dilution of energy. So let me give you some examples. These are all examples of increasing entropy, where energy is going from a more concentrated form to a less concentrated form. So, for example, we know that heat always travels from the higher temperature substance to a lower temperature substance. And think about it. If you have something at a high temperature, that is concentrated energy, right? You could do some work with that, right? If you had something really hot, you could make something happen with that heat. But it spontaneously transfers to a lower temperature. If you have pressure, if you have something that's pressurized, and you allow it to do its thing, it will spontaneously move to a lower pressure. Let's say like a compressed gas in a cylinder. Unless you force it to stay in, if you put an opening, it's going to release itself and end up in a state of lower pressure. And again, so you can think of high pressure as a concentrated form of energy. It could do work on something if the high pressure can push something or expand something. Same with energy. The energy that leaves the power company is a very high voltage, and then as it is transferred along wires and cables to our homes, it ends up at a lower voltage. Some of the energy is lost as heat, some of it's used to power our lights, but ultimately all that energy is end up at a very much more dilute, spread out state. All right, so let's see. All right, so make sure that you can write a sentence or two in your own words explaining what entropy is. The second law of thermodynamics has to do with entropy, and it says that the entropy of the universe is always increasing. Okay, and this is how we show it symbolically. The entropy of the universe is always increasing. Okay, it's always getting larger and larger. And just to kind of remind you, we mentioned before that what we're studying is called the system, and everything around it is called the surroundings. And so when we're talking about entropy of the universe and our thermochemistry systems, when we say that the entropy of the universe must increase, we will have occasions when the entropy of a process or chemical reaction is actually going down, but that's still allowed because as long as the entropy of the surroundings is going up more than the entropy of the system is going down, the net change of the universe is still greater than zero. All right, so the bottom line is to answer that first question I posed to you, and that is, if the energy of the universe is conserved, why do we worry so much about running out of energy? What we're really worried about is running out of useful energy, okay? So we have the same amount of energy available to us, but as I said earlier, when it leaves the power company, it can do a lot of work. It can heat our house up, it can light up all the lights, it can run equipment, but by the time we use it, it's dispersed as heat and all sorts of things and eventually radiated off into outer space and is not very useful. So, what we're worried about is running out of useful, low entropy, concentrated energy. Now, this is just kind of a blow your mind thought. So, if the entropy of the universe, it must always increase, and all of the data we collect so far suggests that is the case. If it's always increasing, getting more and more and more, if we go backwards in time, was there a point in time when there was zero entropy? And what does that mean? Okay. So some scientist has speculated, you've heard of the Big Bang, I'm sure, and supposedly the beginning of the universe was just a very concentrated mass, and there was the Big Bang explosion, which created all the planets and stars and everything in the universe. Well, it seems that you can rationalize that the second law of thermodynamics, entropy always increasing, if you work it backwards in time, that there may have been a time when there was zero entropy, which means everything was packed together in a very concentrated form. All right, so more practical way to think about entropy. The bottom line is you're going to be shown chemical processes, the most common question, and you're going to be asked what's happening to the entropy during this process or chemical reaction. Is it increasing, staying the same, decreasing? So you need to be able to look at the molecules of a system and decide what's happening in entropy. So an easier way to do that is to think of entropy, or one way to think of it is the degree of freedom that a system has. Okay, so the more degrees of freedom, the more freedom it has to move and do whatever it wants, the more entropy there is. And so scientists and statisticians, not to confuse you more, but I just want you to be aware of this vocabulary word, they actually handle entropy in a statistical manner, which you're not going to have to do, but they call each mode of motion a microstate. And so what they say is that the more microstates a system can have, the more entropy it has. And so think about a molecule. I'm just going to call it AB. And let's say that we had a bunch of separate AB molecules, and they were all free to move how they want. They could spin around, they could stretch, they could fly across space. So they would have several microstates or modes of motion. Now, let's say that we had some type of chemical reaction where we combined them and made this long continuous chain. Okay. Now, does the result of that reaction, has it increased the modes of motion? Has it increased the freedom of motion? Or has it decreased the freedom of motion? Or is it the same? Well, it turns out that it has actually decreased the freedom of motion. And so that means it's also decreased the entropy. Entropy has gone down. There's less freedom of motion. And so another way to think of that is if you're just by yourself and you're all excited and you're dancing and jumping and running, you have X number of microstates available to you, freedom of motion. But if you hold hands with somebody else, you're going to be limited in what you can do. You're not going to have quite as many ways of moving as you did on your own. So same with a chemical reaction. So just to kind of test your basic understanding of entropy, I want you to compare each of these sets. Okay? And so what I would recommend is turning off the video, taking a couple minutes and circling the one you think has more entropy or more freedom of motion, and then turn the video back on and I'll explain them. Alrighty, let's see. Let's look at the first set. We have calcium carbonate solid, and we're going to compare that to two compounds combined, like imagine a mixture. One of them's a solid and one of them's a gas. So, first of all, we have two substances, and so the total number of ways of motion of freedom that they have, just the fact that there's two substances is greater than one substance, right? But more important than that is the gas. So what has more entropy, do you think? A gas, a liquid, or a solid? And again, what you should be asking yourself is which has more freedom of motion? Well, a gas has a lot higher entropy, a lot more freedom of motion. Okay? And a liquid has more than a solid. So gas has the highest entropy. And so this B is has a higher entropy. Let's look at these two now. The only difference here is the temperature. So let's see. Do you think water molecule would have more modes of motion at a higher temperature, or less, or the same? It turns out that higher temperature means higher entropy. And that kind of makes sense too, right? You heat things up, you're giving them kinetic energy. They can jump higher, jump farther. They have more modes of motion. So higher temperature means higher entropy. How about these? We're comparing solid crystalline table salt, sodium chloride, to sodium chloride dissolved in water. That's what aqueous means, dissolved in water. What do you think? Well, it turns out that if you don't remember this from Chem 1, it'll be important throughout this semester. Anytime you add an ionic compound to water and it dissolves, that ionic compound, the first thing it's going to do is separate into the individual ions. So, as I said before, if you have separate things, they have higher entropy, more modes of motion than if you have a bond between them and they're held tightly together. So the aqueous solution of an ionic compound always has higher entropy than the solid crystalline form. And finally, let's look at this. Well, let's see. These both have this carbon with 4 bonds. And let's see, I don't know if you remember this, but that means they're both in tetrahedral. So they both have the same shape, but the only difference is fluorine bonded to carbon instead of chlorine. The last example here, I've never totally wrapped my head around this one. I will just tell you the answer. The answer is that the higher the molar mass, or the larger individual atoms are, given everything else equal, will have more entropy. So carbon tetrachloride, chlorine is larger, higher molar mass than fluorine, so there's more entropy. But thinking in terms of modes of motion, yeah, I don't totally get that one, but it's probably worth, or I don't care enough to get it. It's probably worth you trying to remember, though, in case it shows. I don't tend to put it on my test, but in case it shows up on the final. So to kind of give you a summary of the things to look for that can affect entropy of a system, and which will typically be a chemical reaction for us, is the temperature, right? Higher temperature means higher entropy. And volume. That's only when you have gases, and pressure and volume. We'll go over that a bit later. the phase that you're in, right? We know that, again, gases have higher entropy. Mixing, so the probably easiest example to remember is when you dissolve an ionic compound in water, it has higher entropy. And of course, the composition of a compound itself. All right, so let's look at each one of those effects briefly. Now, this is kind of letting you look at the statistical approach to entropy. Remember I said consider every mode of motion a microstate. And so each of these energy line represents what we're calling a microstate. So I think this is kind of a neat way to put it. So when you heat any substance up, you have opened up extra energy levels, right? You've given them more energy so they can do some things at higher energy levels that they couldn't do at a lower temperature. So again, the more they have more freedom, more modes of motion, or more microstates to a statistician, so therefore higher entropy. And of course, make sure you remember that gases do have quite a bit higher entropy than liquids, which are in turn have higher entropy than solids. That's kind of intuitive, I hope. All right, mixing things together. All right, let's talk about mixing, which is a little bit trickier to understand, but I think you will in a couple of minutes. So let's say that we have a container of dye and a beaker of water. What would have a higher entropy, the two unmixed or the two when they're mixed together? So again, I think thinking of it as freedom of motion in the case of mixing is not helpful unless you're dissolving like an ionic compound of water. But if you're just generally mixing two things together, it might be helpful to think about the statistical approach. Again, I'm not likely to ask you much, if anything, about the statistical approach, but it may be on your finals. So, all right, so there's a little statistical easy activity to kind of help you visualize this. So we're just going to call this our flask, right? So just pretend that we have a beaker or flask that has 4 segments in it. And, all right, then let's say we're going to call dye molecules this blue dot and water molecules this structure. And we're going to put into our container, our beaker, 2 dye molecules right here and 2 water molecules. And they're not mixed yet. Okay, so we're going to call this the unmixed sample. All right. So let's say we start mixing them. Okay. When we start mixing them, these 4 molecules are going to kind of randomize their way around that beaker that they're in. And so what a statistician does to figure out entropy is it figures out how many different ways can these particles that are here be arranged, okay? How many different ways can you arrange these 4 particles in this beaker? And each arrangement like this is called a microstate. And so the more microstates you have, the higher the entropy is. So let's look. Okay, so if you drew every possible arrangement of those 4 molecules in these 4 sections of the beaker, you would get 6 possibilities, 6 microstates. Okay. And remember, the unmixed was only this. Okay. So what has more microstates? Okay. The unmixed only has 1, and the mixed has 6 possibilities. So we can see that mixing something increases the entropy. It's easier to see from a statistical viewpoint. So the more likely state of the system is always the higher entropy. Okay, the more likely is the higher entropy, because remember, the universe is always moving towards higher entropy, just spontaneously. So the higher entropy state is the one that has either more freedom of motion or more microstates, right? Either way, whatever, some are easier to think one way and others the other way. And the one that has more microstate is the mixed state, okay? So the mixed state is the one that has higher entropy. Okay, that's a little bit weird, but all right, so this is the effect of molar mass, okay, or atomic size, or sometimes you'll see it described as molecular complexity. And that was the example we had was carbon tetrachloride versus carbon tetrafluoride. And carbon tetrachloride had higher entropy. So compare this simple compound, nitrogen monoxide, to nitrogen dioxide and then dinitrogen tetroxide. Which one has the highest entropy? And these are examples of what of substances we would say are increasing in complexity. So the nitrogen monoxide would have the lowest complexity, right? And as you add more atoms, the dinitrogen tetroxide would have the highest complexity of these three. So what this says is that the larger a molecule or the higher its complexity, the higher the entropy. And by looking at these figures, I think it's pretty obvious. The nitrogen monoxide, if you count up all the different ways it can move, once you add another atom, so now you have 3 atoms instead of 2, you have many more ways to move. And again, if you have 1, 2, 3, 4, 5, 6, you're going to have even more ways to move, and that's why it has the highest complexity and the highest entropy. We've talked about the first 2 laws of thermodynamics, and I'm just going to quickly mention the third law of thermodynamics. It's kind of the weirdest one, I think. It simply says that the entropy of a perfect crystal, so tightly packed solid crystal, at absolute zero, that's 0 Kelvin, is 0, okay? What does entropy equal 0 even mean? It means complete lack of movement. So scientists think that the only situation which would result in complete lack of movement of any of the atoms or molecules, it would occur at 0 Kelvin, absolute 0. But it turns out that for theoretical reasons that I don't completely understand, scientists believe that it is theoretically impossible to reach absolute 0. But they've gotten really close and done quite a bit of studies that kind of support that would happen. All right, so that's it for entropy. And so we have learned about enthalpy, which was change in enthalpy, delta H. And we just talked about entropy, which is abbreviated with an S. And when you put those 2 together, you get something special called Gibbs free energy. And it's important to understand what free energy is. It's the energy available to do work. Now, I talked briefly about, even though energy is conserved in our universe, there's useful energy and there's non-useful energy, right? And so we want a low entropy. We want concentrated energy. That's the type of energy that can do work. And that's why understanding Gibbs free energy is really important, because Gibbs free energy is the only type of energy that is useful to us. So the equation that you need to know, commit to memory, is that Gibbs free energy, and that's abbreviated with a G, equals enthalpy minus temperature, and that's got to be in Kelvin, times entropy, okay? So both enthalpy and entropy affect Gibbs free energy, or energy available to do work. Now, you do not need to be able to derive the Gibbs free energy equation. I tend to always put derivations in case anybody is just randomly curious, but you do not need to know this unless you just want to. All right, so Gibbs free energy has a lot of uses for us, but one of the most important uses is it can tell us whether a process is spontaneous or not, okay? What does that mean? Well, spontaneous simply means that a process will occur without outside intervention. A spontaneous process occurs on its own without you having to go up and do anything to it, okay? So what are some things that are spontaneous? Well, an ice cube will melt if you take it out of the freezer and put it on the kitchen counter. So melting of ice is spontaneous at room temperature. We know that rust is a spontaneous process if we leave some types of metal outside. And so, again, anything that occurs on its own without you having to do anything is a spontaneous process. I want to mention one other thing about spontaneity, and that spontaneity says nothing about the speed of a process, okay? It only says whether or not it's going to happen without outside intervention. Nothing about speed. So we have some spontaneous processes that happen like right away within a matter of seconds, and we have others that occur slowly over years. So again, spontaneity tells nothing about speed. All right, so back to our famous equation for Gibbs free energy. Again, Gibbs free energy, or the energy that is useful to us, depends both on the enthalpy of a system and on the entropy. Both enthalpy and entropy are forms of energy, as is Gibbs free energy. They are all types of energy. All right, so I said that we use Gibbs free energy to determine the spontaneity. How does that work? It turns out that when delta G is negative, okay, less than 0, okay, the process is spontaneous. So when the Gibbs free energy that we calculate from that equation has a negative value, that is a spontaneous process. And similarly, if Gibbs free energy is greater than 0, if it has a positive value, that is a non-spontaneous reaction. Now, kind of interesting, if you have a process A going to B, and if it is spontaneous in the forward direction, if you were to run the reaction in the reverse direction, like start with B and try to get A, it would be non-spontaneous in the reverse direction. All right, so again, we want delta G to have a negative value. Chemists want spontaneous reactions. They want to happen. They're cheaper to have happen. They're more efficient, more productive. So chemists really look for a delta G that's negative. So let's look at all the combination mathematical signs, plus and minus, for these three energy terms, and see under what conditions we would expect to see a spontaneous process. So if enthalpy and entropy are both energetically favorable, that means that delta G will also be favorable. So we're going to talk carefully about signs in this slide. I mentioned a couple days ago that the trickiest part of thermal chemistry for most students is keeping the plus and minus signs straight. So here we're beginning here. Be very careful. I said already that a negative free energy means spontaneous. So I'm going to put that here. When delta G is negative, it's favorable. What about enthalpy? What does nature want? What's a favorable energetic state for enthalpy? It's also negative. Okay, we want energy to be nature wants energy to be as low as possible. It's more stable. So both of those should be negative. Now, the only rebel is entropy. Entropy, when it's favorable, remember the second law of thermodynamics that says entropy always increases? So the favorable value for entropy is positive. So this is a situation. So again, let me restate this. When enthalpy and entropy are both favorable, that is when enthalpy has a negative value and entropy has a positive value, then delta G will always be spontaneous, will always be negative. Okay? Now, also, if delta H and delta S are both unfavorable, so what does that mean? Okay, delta H is unfavorable or endothermic has a positive sign, and entropy, when it's favorable, has a negative sign. Okay, and when you use those signs in this equation, you will always get a positive value for free energy, which means you will always get a non-spontaneous process. All right, so those are intuitively not hard to understand. What's tricky, what happens if enthalpy is favorable, for example, and entropy is unfavorable? They're both important in determining free energy. What if they're fighting with each other? It's like a tug of war. Who wins? Are we going to end up with a spontaneous process or a non-spontaneous process? It turns out that in these cases, when one is favorable and one is not, the tiebreaker is temperature. It all comes down to temperature. I'm going to review all the different mathematical sign possibilities for the Gibbs free energy equation. So this is another possible conceptual question that you might have on an exam to explain the table that I'm getting ready to create. So if delta H and delta S are both favorable, which means delta H has a negative sign, delta S has a positive sign, then delta G will also always be favorable with a negative sign. And the process will be spontaneous. Now, if all the values, if the enthalpy and entropy are both unfavorable, which means delta H would be positive, endothermic, delta S would be decreasing, getting less entropy, or negative, and delta G would always be unfavorable. Okay, if enthalpy and entropy are both unfavorable, there's no choice. Delta G is also going to be unfavorable. So it will be a non-spontaneous process. Now, the tricky part comes. What happens if enthalpy is favorable and entropy is unfavorable? Okay, so you'll notice that the tricky ones to understand are when the signs of delta H and delta S are the same. So if one's favorable, one's unfavorable, delta G can possibly be spontaneous or negative, but only under certain conditions. What's the only other variable in this equation that might affect free energy besides enthalpy and entropy? Well, hopefully you mentioned or thought about temperature. So it all is going to depend on temperature. And notice that temperature is linked with the entropy term. So when you change temperature, you're only going to change the entropy term. Okay? So let's look at the situation I just gave. Okay? Enthalpy is favorable. Entropy is unfavorable in this case. Okay? So if you increase temperature, you're increasing the importance of an unfavorable variable, okay? So we don't want high temperature, okay? We want to minimize the unfavorable part of the equation. So we're going to say that it is spontaneous, but only at low temperatures. All right, now the other situation where there's a tug of war going on between enthalpy and entropy would be if they're both positive, okay? So that would mean that enthalpy is unfavorable and entropy in this case is favorable. So which one's going to win? Well, our favorable term this time is entropy, so we want to maximize the importance of the entropy. How do we do that? By raising temperatures. So in order for this scenario to be spontaneous, we have to have high temperatures, okay? So this is the table that's good probably to jot down, make sure you understand it, make sure that you could explain these last two scenarios to me. Now, this is a little bit of a tricky concept, so you may have to listen to this slide and the next couple comments a couple of times for it to sink in. And onward to the last slide. I mentioned before in the course that there are a lot of graphs, and graph interpretation is really important. And so this is a graph of Gibbs free energy. Notice that along the y-axis is Gibbs free energy, G. Now, G is simply the free energy of a system. Could be an atom, a molecule, a couple of molecules. Delta G, which is what we've dealt with so far, is the change in free energy, okay? But I want you to look at the y-axis. It's not delta G, it's just G, free energy of the system. All right, so, and this is reaction progressing toward the right. So if we're going downward, if the free energy of a system is going down, 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 that means that free energy, or the change in free energy, is less than zero. That means it's decreasing, okay? So if you were to look at a free energy graph and it was going down as the reaction proceeded, that would mean that is a spontaneous process, okay? Anytime delta G is negative, remember you have a spontaneous process. Okay, on the other hand, if you look at a Gibbs free energy curve and the energy is increasing, okay, or greater than zero, so it's getting more and more positive, that is representative of a non-spontaneous process, okay? So you want to be going down to be spontaneous in free energy. Now what's this at the bottom? Right here at the bottom it says change in free energy is equals zero. Well, it turns out that looking at just from a graphical point of view, when you're down here at the bottom, just moving a little bit left or right, there is no change in free energy. Now remember, free energy is the y-axis, so if you're moving horizontally, there's no change in it. But the more important thing to realize is that delta G equals zero means that there's no driving force to do anything, okay? It's not spontaneous, but it's not non-spontaneous. So exactly what is it? Well, we call it equilibrium. So anytime you see delta G equals zero, that means that the energy of the system is the lowest possible point, and it's the most stable there, so that's when delta G is zero. There's no driving force, and that occurs under all equilibrium positions. So anytime you hear about a process reaching equilibrium, it means that delta G is zero. There's no driving force for it to do anything but stay right there. That's it for entropy.